Thank you very much. It's always a great pleasure to be here. I have the privilege of spending quite a bit of time at this institute. We lost John Brooker. So the title talks about solitons for nonlinear cubic Klein-Gordon. I will get to this eventually, but I'll of course give you a much bigger background. So what we'll talk about are equations of what one might call, maybe Tom, you can correct me, classical field theory. Like phi to the 4, but on the line. And what we start from a Lagrangian. Lagrangian is a space-time integral, so RTX. And we have minus a half phi t squared plus 1/2 phi squared plus w phi dx dt. And formally, it is a formal integral if you want, but it is meaningful to look for the critical points of the action. This is not too elementary for the audience. So we look for the critical point of the action, and then we obtain a wave equation on the line. Where phi is a function of t and x. And we're interested in the Cauchy problem. So we give initial data, and we want to solve forward in time. Associated with this wave equation and this Lagrangian, there is a conserved energy. So we have E of phi is now a perfectly meaningful and finite integral. That's a requirement that this integral is finite. Dx. So I will not write phi of, so phi of course is phi of tx, and I will simply not write explicitly. And what are the main examples that we are interested in? There are 3. You could, of course, and this being done, that this can be considered in for many different types of W. For the purposes of this talk, we will have 3 different types of W. One is this one here. This is called phi to the 4. And I will write these PDEs explicitly for these 3 models in a moment, for these 3 different potential energies. Another one is cos 1 minus cosine phi. That is called sine-Gordon. And most relevant for us is NLKG 3, and there we have 1/2 phi squared minus a quarter phi 4. Okay, these are the 3 different models we want to look at, and the pictures that go with it. Let me just draw the first one and the third one to the best of my ability. All right, so this looks like that, and this looks like this. Notice something curious, that W of 0 here is a quarter. So the 0 solution of phi 4 has infinite energy. So you cannot solve around 0, add 0 for the phi 4 model, it's meaningless. But here, of course, it's eminently meaningful. And this, you understand, is just the potential energy of the physical pendulum. So what are the 3 PDEs? You then have, there are, I'll just write them down. So let's start with, be consistent and start with phi 4 in the same order. So we have minus phi plus phi cubed is 0. Then we have phi dt minus phi xx plus sine phi is 0. That's sine-Gordon. And then there is, as in the title, the cubic Klein-Gordon. Notice this confusing choice of signs. It's really worth emphasizing that this minus sign looks tremendously dangerous, because if you Fourier transform, you will see that the symbol, formally speaking, of this is phi 4, this is sine-Gordon, this is NLKG3. I should capitalize the k also. So here the dispersion relation would be plus psi squared minus 1. Yeah, but this is not positive definite. So for small psi, it looks like the equation changes type. It suddenly switches to elliptic, which would mean that you have here an elliptic symbol. So this makes absolutely no sense. This is supposed to be a wave equation. So what is the resolution to this? Well, it has to do with topological solitons. These two have a notion of a topological soliton. Here one doesn't typically speak of a topological soliton. Here there is just a soliton. And you understand these different notions by looking at the phase portrait of the stationary solutions. Stationary equation. If you look for stationary solutions, phi tx, which are, let me abuse notation, just write phi of x, so time independent. Then you obtain just equations without that. You can see multiply them by phi index x, so by the x derivative of phi. I should just say multiply them by phi prime. Integrate. For example, if you do this for the first one, and I won't do it for all, don't you get this? This has to be a constant, right? All right, so what are the phase portraits for these three different, and you can do this obviously for each of these second order ODEs just on the line. What are the different phase portraits? So I have to concentrate here. So for phi 4, they will look like this. Clearly you have a stationary solution which is -1 and +1. This is 0 anyway, this would be 0. Here you get +1 -1. Okay, so you see that the phase portrait connects these equilibria. I should draw them in a color. Here you have an elliptic and it's supposed to be perfectly symmetric, which of course I have difficulty drawing. And here you have, if you linearize, you have a pair of positive, it's hyperbolic, so positive eigenvalue, negative eigenvalue. So you have unstable and stable manifold. And then the rest of the trajectories look like this. Agreed? And in color, this, so this is -1, this is 1. We're interested in this heteroclinic orbit connecting these equilibria. And in fact, because you can separate variables here, this has an explicit formula. It is for phi 4, it's tanh x divided by √2, if I'm not mistaken. It connects -1 to +1. Okay, so this is an explicit solution of this ODE. It connects two different states of -1, 1. That's why it's called, first of all, it's a kink. This is what one calls, this is phi to the 4. This is one of the famous kinks. You have a kind of an anti-kink, right, connecting 1 to, so this is -1 to 1. You can put a minus, then you connect 1 to -1. They have non-trivial topological charge. These are just words from field theory. If you play the same game with this equation, then you just recover the phase portrait of the pendulum, and we arrange the angles so that here actually you have these infinitely many heteroclinic orbits connecting in, so even integer multiples of pi. And they, of course, have explicit formulas. And here the kink of sine-Gordon is 4 times arctan e to the x. So this is the kink of sine-Gordon. Notice here too, we connect two different constants. For this model, let me put the phase portrait of cubic Klein-Gordon over here. The phase portrait looks completely different. Here we want to connect 0 to 0. The phase portrait turns out to look like this. I'll try to be very precise. You have two homoclinic orbits connecting 0 to itself. Here you have again -1 +1. That doesn't go away, but they are now elliptic. And then the rest looks like this. Okay, and in color, So we have all sorts of colors here, amazing. So here we have, this was not good, the kinks. And so I drew one of them. And here we have the homoclinic orbit. And there too, we have explicit formulas. And here we don't write K. The tradition is to write Q, and this is root such X. Okay. All right. So now, of course, I should make a few comments. Where is the PDE? This one is special. I should put a box around it because sine-Gordon, this one, is completely integrable. And it was actually written down the first time in the 1860s, I think, in geometry as a sine-Gordon. So sine-Gordon as a Gauss-Codazzi equation of the pseudosphere, discovered by one of the French geometers. It has very special features that are absent here and absent here. So these are not completely integrable. So I will now launch the topic of most interest to this talk. So what we care about is the stability theory of all of these solutions. So stability, the basic underlying question, and for 5.4, the asymptotic stability theory of this explicit tanh kink is unknown. It's a very delicate question. I will try to convey to you why. Okay, so the question is stability versus asymptotic stability. Of kink and or soliton, right? Depending on whether you have a K or a Q. Now, so what should we do? We look for the perturbative equation. So we're going to write phi minus K or Q as some small function u. And so please bear with me as I write down, this can go now, as I write down the perturbative equations for these three models. Where's the big one here? They're, of course, completely explicit. So now we want the perturbative equations governing U. Again, I will try to stick to this order of phi for sine-Gordon and nonlinear cubic Klein-Gordon. We have UTT plus HU, so this will be the linearized operator. And then we have a collection of nonlinearities. I shouldn't even do this, which take the form quadratic plus cubic and possibly higher orders. So 5.4, you have quadratic cubic for nonlinear Klein-Gordon, quadratic cubic for sine-Gordon. Of course, you have all terms. And these are smooth coefficients. So alpha, beta are either localized, meaning that they're Schwartz functions, all right? Or they are like a tanh. And in our three models, this tanh happens exactly for 5.4. So then you have a non-local term here, all right? And that's the nonlinear level. I will, of course, begin with the linear level. So now I need three different expressions for H. They're 1D Schrödinger operators. So they look like this, D squared. And now for 5.4, you get 2 minus 3 sech squared x divided by root 2. for a sine-Gordon, you get minus the Laplacian, then you get plus 1 minus 2 times sec squared x, and for cubic Klein-Gordon, you get minus del x squared plus 1 minus 6 times sec squared x. All right, again, this is the linearized operator of phi to the 4, linearized about the kink k, which is explicit tangent x over root 2. That's why x over root 2 here. This is sine-Gordon. And this is NLKG3, cubic, nonlinear cubic Klein-Gordon. If you want to study the stability question, I didn't even say what I mean by this. It, of course, the most natural thing to look at is in the energy class. If you take a solution of finite energy and you look, you take the kink and just look nearby in energy for data, and then you run the evolution and you want to know what happens in a long time. Do you stay near this? This turns out to be a relatively easy question. I'll give you the answer in a moment. It was obtained in the 80s. Let me return to this feature that I highlighted for a moment, that the potential energy for phi-4 at 0 is a quarter. So 0 solution is meaningless for phi-4. It has infinite energy. You see, the kink doesn't have this problem. The kink kind of goes over this mountain. It connects minus 1 to 1, and it beautifully has finite energy.
All right, well, let me just ask, so in the last question, when you had this, what did you call it, nonlinear?
This is nonlinear Klein-Gordon.
Yeah, so that won't have global solutions, will it? I mean, if I start with large data, I'm going to be in trouble, right?
Yes. So this, careful. So this thing, this thing can blow up because the linearized problem has a negative eigenvalue. We'll get to that. That's why we'll need a manifold. For these two, you have global solutions for any data.
But you don't have a global solution for the last one.
This can blow up.
Yeah.
That is why our stability theory will involve a syntestable manifold.
Okay.
So now we have these 3 different operators. Let's draw spectra. What is the spectrum for phi-4? I claim, and it's very easy to see, you have a 0 mode. Not easy to see is that you have an internal mode, and then you have the continuous spectrum starting at 2. So this is the phi-4 spectrum of H. For sine-Gordon, you again have.
So the 3 halves is a bound state that comes some kind of.
This is an extremely interesting thing that makes phi-4 really extremely difficult. It has an explicit formula. We'll get to that if I remember correctly. Sec tanh of x over root 2, so it's localized, of course. Here you have sec squared, okay? And this is something like 1 minus sec, something like that, sec squared.
So there's a point there. I mean, there's actually
3 halves.
The point, but what about at 2?
At 2, you have a threshold resonance.
You have a threshold resonance.
Absolutely. And you will recognize each of those can be reduced to hypergeometric equations by a tanh substitution. So that means that they're of the Peschel-Teller hierarchy. I will write this down in a moment. They are miraculous operators. If you change, for example, here, the power, you lose this. Okay? So if you go to phi to the 6, which is actually a better behaved equation, you would think it has more dispersion. So phi to the 6, then you do not have Peschel-Teller. You don't have a 0 energy resonance. And all of them actually reflectionless. The reflection coefficient is 0 for all energies. For these.
Oh, yeah. Those are the linearized ones have.
So these are linear Schrödinger operators on the line. They're all reflectionless for all energy. But so far, I've not been able to exploit that they're reflectionless. One, this is sine-Gordon. The spectrum is continuous. At 0, you have a mode, and why you have a mode might be obvious to you. It's because of translation symmetry. So just let me write down the. Now, Tom, here you have, I think it is minus 3/4. You have a negative eigenvalue. And then you have 1, 0. Again, you have a threshold resonance. So this one makes you exponentially unstable. And I can't say because of that you blow up in finite time, but yes, you can blow up in finite time for focusing. So why do you have eigenvalues at 0 always? Well, simply because if you take H and you apply to it K prime, you must get 0, right? Because the entire problem is translation invariant. So if you differentiate in the translation, the linearized problem has a 0 mode. What is tanh prime? Isn't it sech squared? Yeah. So therefore, we see that for the picture is for phi4. So phi4 has a 0 mode coming from translation symmetry, which is sech squared. Do you want to guess what the 0 mode is here for sine-Gordon? The kink is 4 times arc tan e to the x. You have to differentiate 4 times arc tan e to the x in your head. You get sech. You get sech. So here you have the sech, again, translation mode, hk prime. And here, of course, you have hq prime is 0. Okay. But you can also simply check that there has to be negative spectrum because the Rayleigh quotient, which is just this inner product, I don't need to divide by the internal of q squared, is negative.
Yeah.
You can just check it, okay? And therefore there has to be negative spectrum. With some more work, you can conclude that there is actually, it follows from Sturm oscillation. Why? Because q prime, sech prime, has a unique 0. And so then it has to be the second eigenvalue, and the ground state is strictly positive. So just by Sturm oscillation, you know, there is unique simple eigenvalue. Here is the second eigenvalue. Then you can verify that this is, there is a gap. And here, these thresholds are highly special. They are non-generic. So you really,
Is there an eigenvalue? Is there an eigenvalue actually there as this 0 or 0 resonance here? Yes.
so these types of operators can never have eigenvalue at the threshold, at the end of the
No,
continuous.
but there's a solution which is
Bounded but not L2.
okay.
Just by looking at the scattering problem, the perturbative scattering
That's a
problem.
0 or like a 0 energy resonance, right?
That is a threshold resonance, exactly. So let's, since we just started discussing them, let's continue.
Do they all appear in all these thresholds?
All of them. And in fact, these are all part of something called the Peschel-Teller hierarchy. This goes back to the beginnings. I hope I'm not misspelling anything. Peschel-Teller hierarchy. And since I am using this expression, I should tell you what this hierarchy is. It's of the form HL. It's minus del squared. I don't need to shift the spectrum by adding the constant. I'll just do this, minus L plus 1, sech squared x. And now the magic here is that if you introduce a first order operator, a family of them, you can write them, you can conjugate this to the case of 0 potential by a bunch of first order differential operators. That's algebraic miracle. And DL is del x plus L tanh x. And then the claim is, which you can try verify, that HL DL minus 1 D1 equals D1 DL this. No potential.
Wait a minute.
The L. It's supposed to be an L. So this is an nth order differential operator. If you apply it to the second order operator, it kills the potential. Sorry, other way around.
Okay.
Other way around. Sorry. Okay. Blackboard blindness. Sorry. Blackboard blindness.
Now,
Yeah. You should have immediately shouted at me.
yeah.
Blackboard blindness. So you can commute these through and then you kill the potential. That's amazing, an amazing property. Another way, the way this manifests itself, of course, one should start with the case L equals 1, a single one, which is the sine-Gordon case. You see, if you look at H1, that's what sine-Gordon gives you, linearized sine-Gordon, you get this twice sech squared. This has the property that it maps y0 to minus y0 because my h1 didn't shift by the 1. So the translation mode is this minus y0. So h1 plus 1.
So what is y0?
Y0 is the derivative of the sine-Gordon kink, which is sech. So y0 is sech. Okay. And notice something that h1 plus 1 is now non-negative, and it's not unnatural for us to try and factor it in the form d1 star d1. And what is d1? d1 should have the same kernel as h1 plus 1, which is y0. Okay, so how do we generate a first order operator that eats y0? Well, what we should do is y0 inverse del x y0, because then del 1 y0 is del x1, which is 0. And lo and behold, that thing should give us this. Maybe I was wrong with the minus here, forgive me. So that is exactly this tench, okay? And if you think of the Euclidean algorithm, this gives you a non-negative operator. So what is the remainder if you divide, quote unquote, this by d1? Well, you get d1 star, and you could only get a 0 order operator, which makes no sense because y0 is in the kernel. So just by inspection, it has to be true because both are non-negative, you see? And d1 star d1 then has to equal this. These types of games you have to play to actually prove this claim. This is
these work for, I mean, are these
only partial teller.
Are these special to quartic type interactions, or can they work for other nonlinear?
Well, sine-Gordon is not per se quartic.
No, I know, but that's integral.
That's completely integral. So
suppose I pick another potential.
If you pick a random one, it doesn't fit into this hierarchy. And then you are actually in a better situation because you don't have a threshold resonance.
Things are easier there some ways.
In many ways, this is why the literature, which has really exploded over the past 20 years, and we have a key contributor, Hans. Early years ago, Hans already started with Avi and Sterber, and actually Igor working on these types of models. But you see, you won't be surprised to hear that on the left, you assume that you have a 0 potential. Yeah, of course, you want to be able to use the free Fourier transform and not the Fourier transform based on a potential. Now, the reason that I'm mentioning these Darboux transforms, this is called Darboux transform, it's because in my work, I joined this game late. It was with Avi and Hans, we wrote a paper, and Luehrmann, and then with Luehrmann, we wrote 2 papers, and the second one with Jonas, I'm reporting to you on today. So these Darboux transformations play a crucial role because they reduce you to the case of no potential on the left. So think of it in this way. It is very natural to study the stability of vacuum solution, the 0 solution, right? In that case, you generate no potential on the left. For phi-4, that is a priori meaningless because the 0 solution has infinite energy, it's out. So phi-4, if you have any stability question, it has to be the one near the kink. And once you have a non-trivial object that you're perturbing around, you will generate a potential on the left. And then you are faced with these spectral questions. What is a Darboux transformation? It just means that you don't work with these equations. You hit them on the left. For the case of sine-Gordon, we just hit them on the left with 1 copy of D1. But then you have to hit the nonlinearity with 1 copy of D1, right? And you will see that. So I'm getting a bit of ahead of myself. I might return to the Darboux transformation because there is a very explicit way to invert them. And so then you have to express the right-hand side as a combination of derivatives and integral operators. That's the price you pay for killing the potential on the left. All right. But now, what about the orbital stability question? Maybe I haven't even written that yet. That was settled. How am I doing on time? Not great. Orbital stability question was settled in 82. I hope I remember the names. Henry, Perez, Brzezinski. Forgive me if my spelling isn't perfect here. And they simply observed that the energy, if you remove the translational mode, the energy is coercive, right? Because look, and when the energy is coercive, so here is what they noted. Take the linearized operator, for lack of better notation, I'll call it H again. U controls the energy. Look at the pictures. Norm U H1 squared, provided U is perpendicular to the zero mode. So I'll just say the kernel of H. And U, of course, has to be in H1, because that's the energy graph. And then the energy becomes a Lyapunov functional, but when? If you mod out the translational symmetry, right? Because modding out the translational symmetry is the exact way to remove the zero mode. So now I've proved the theorem to you, basically. And the theorem has to be that kinks and the soliton, well, soliton cannot work. For that, you need, look at that. So I forgot this, of course. And for this, you need a center stable manifold that introduces a codimension one condition. All right. So the theorem I'm about, this was silly that I drew the red line down here. Because of that, the red line has to stop here. So for the models without negative modes, we proved the theorem. And it is precisely the orbital stability theorem from, well, 40 years ago. And it says this theorem. Given epsilon, there exists a delta such that if your initial data for the field are of the form k plus u0, u1, k is the kink, and what are u0, u1? They should be small in h1 cross L2, less than delta, right? So this is this Henry-Perez-Brzezinski here. Then, for all times, phi of t minus k, but I have to, well, I shouldn't be so lazy and write arguments here. For x plus y, if you want, comma, phi dot of t in h1 cross L2 less than epsilon. And here is inf in y in the real line. I kept this here because that infimum ensures this. So this is, again, how do you do it? Well, you use this as a Lyapunov functional. And of course, this is conserved, right? You have a conserved energy up to small errors. So you use the full nonlinear energy. This isn't the full nonlinear energy. You have to throw in higher order terms, which have smaller order. They're controlled by the. All right. So here ends the orbital stability. And for that, well, for that, you have to do center stable manifolds. Now, what about asymptotic stability? Let me write down a theorem. And this is very much an ongoing story. So there is this remarkable work, Martel, Munoz, and Kowalczyk. This was, they first circulated this in 15, it appeared in 17, and then Martel and Kowalczyk revisited this topic and removed some kind of numerical dependence of this work. So there were some calculations, some spectral calculations you had to a little bit computer assisted. This was all removed here. And this is for phi 4, where you do have this internal mode. Now, why is this internal mode bad news? So what does it mean? Here you have h of sech squared is 0. Here you have h of sech tanh. I should write h minus 3/2 of sech tanh is 0. And here you have, we'll get to that, a threshold resonance, which is L infinity, not L2. You cannot have L2 there. And look at these functions. This, because the potential is even, the ground state is even, z squared. This is odd. This function is going to be even. So you have even mode, odd mode, even mode. What they observed is that there exists an epsilon positive such that, just like before, I will not, just to save time, not recycle everything over there, such that if norm U0, U1 in H1 cross O2 is less than epsilon, and they are odd, because if they're not odd, the creature starts moving, and you also see the threshold resonance, then you have asymptotic stability of the field. But in red, I cannot emphasize this enough, on a compact interval, tends to 0 as time tends to infinity. Of course, this is false with I compact. Of course, this is false if I is the real line, because the energy is conserved. The distance is not going to shrink. What does this say philosophically, or in fact, quite precisely? It says that if you are an observer looking only at a compact interval on the line, that in infinite time, if you perturb the kink a little bit, you will see the solution collapsing to the kink, and the perturbation, the energy radiates off to infinity. But it has other profound implications. It says, for example, yeah.
Couldn't you have a slowly moving kink?
No, because it's odd. This result is, that's why this cannot work for general perturbations. You could say, well, then we have to translate this, but their method, which is based on relatively soft tools, in the sense it's ingenious, but they use virial identities carefully crafted. So it's based on some clever Laplace functionals, which is all the more surprising because of this internal mode. And why is this so remarkable? Because you agree with me, right? That the internal mode on the linear level leads to a harmonic oscillator. You are in the positive spectrum. So therefore you oscillate cosine sine of t root 3/2. That doesn't decay. So this seems to be in complete contradiction to this, because this says that locally you will approach the kink. Clear? So on the linearized level, asymptotic stability is false. So what is so remarkable that there is a coupling of the internal oscillations via a nonlinear effect, Fermi-Golden rule, to the continuous spectrum. Okay? And
so you need a nonlinearity. Yeah.
Only the nonlinearity couples you through multiplication of oscillations, right? It pushes this over here. And in fact, you see here that what's important is 2 times root of 3/2, which is the quadratic effect on the internal oscillation, is bigger than 2, that it lands you in the continuous spectrum. The pioneers of this is a remarkable paper by Sofer Einstein from 1996 or 7 in Invenciones, where they, on a 3D model, 3D because it has much better decay properties, so they take a 3D nonlinear Klein-Gordon with a cubic nonlinearity, so they take a cubic effect, and they have a internal mode by bifurcation theory, and they show that there is a slow damping that's governed by a Riccati equation. It's a highly non-trivial, they use normal forms, which means integration by parts in time, etc., etc. Absolutely beautiful, please look at it. So that makes this 5-4 so special. For sine-Gordon, can this be true or false? For sine-Gordon, it cannot be true due to a remarkable creature that the sine-Gordon as a completely integrable equation has in their so-called wobbling kink. Sine-Gordon admits solutions that look like this and which wobble like that periodically. You understand, right? They go above and below the kink like a clock periodically. And if you have that, well, then you never have this. So for sine-Gordon, this is false. Their method breaks down completely in the general case because of threshold resonances. Because you see, when you're odd, you're perpendicular to this mode. And since I keep talking about it, I should explain more, and then really I'll have to start speaking. I'm allowed to go to 4, correct?
Yes.
Did I write down what the resonance function looks like? I think so. It's 1 minus 3 half z squared. If I'm not mistaken, this is 1 minus 3 half z squared. So h minus 2 of 1 minus 3 half z squared equals 0. Notice this peculiar feature that this function approaches 1 at both ends. So what's really going on, let me launch into a brief digression here. If you have a completely general shading operator on the line with a potential, and just assume that the potential is nice. I could write a Schwartz function, but actually everything I say remains true. If I am in a beta class, I need to be in, how to write this, x minus 1 L1. So xv has to be in L1 on the line. Or you just pretend it's a Schwartz function, which is good enough for us. Then you look at these solutions, which are psi squared f plus minus x psi, which have the property that f plus minus x psi are asymptotically equal to the free waves, to plane waves. So as x tends to plus minus infinity until you put plus minus. All right. These are the famous Yost solutions. So Yost solution. And of course, the model we should have in mind is that V does this, and then you send in an incoming wave. Some of it gets reflected, and some of it gets transmitted. You've seen these things before. You have a reflection coefficient, a transmission coefficient. In formulas, they look like this, that you have an F minus of x minus psi. That's the incoming wave. Then to it, you add the reflected wave, which is F minus x psi. And this depends on psi. And this will have to equal the transmitted wave, which behaves like the plane wave at plus infinity, so you have this. These are the relations between transmission and reflection coefficients. What is a zero energy resonance? And by the way, the Wronskian, so a key player in all of this is the Wronskian, W of psi, which is the Wronskian of F plus and F minus at psi. This is never 0 if psi is different from 0. However, because of my x v in L1 assumption, this is continuous as psi tends to 0. And you know what happens as psi equals 0. You have a fundamental system. Let me just write here because we can cover this then. If you look for solutions equal 0, well, then at infinity, you should have a fundamental solution, which is 1 comma x. So solutions are either linear. So you understand, right? This is all very simple. So if you have minus f double prime equals 0, then here is your fundamental system of this equation. So at 0 energy with a decaying potential, what you can have are, if you send in a constant here, 0 energy means you send in 1. Generically, you will end up with x minus x up to a constant. You'll end up with cx or some other constant like this, all right? Generically. But in special cases, you will be able to connect the constant on the left to the constant on the right. This is called a zero energy resonance. But from the picture, you can never be L2. Because how can you build L2 from 1 and x? Okay? So that's a threshold resonance, and it's equivalent to a number of properties. Why is it called resonance? Because there is a small divisor hiding here, and the small divisor comes when you look at the Laurent expansion of the resultant in the complex plane. Okay, and the Laurent expansion of the resultant in the complex plane will never start for such an H with a 1 over z squared. It can only start with a 1 over z, and if it does so, it comes with some constant, and then a projection, quote unquote, it's not an L2 projection onto the resonance function. So H by 0. Okay, that's the threshold resonance. And then plus a big O of 1 In which sense? In some weighted L2 sense. Not in L2, but here you have some weighted L2, okay? As z tends to 0. It's Luehrmann expansion. You cannot start with 1 to the 3rd because that would mean you have a 0, an L2 function that solves this, which from this picture you cannot have, all right? And here is your small divisor. That's why this is called a resonance. And we observe that phi is in L infinity, but not in L2. So the enemy, quote unquote, the generic case, the free case, of course, is resonant. Generically or non-resonant. It means, by what I just said, that the Wronskian at 0 is 0. And the transmission coefficient, there is a formula for it. It's minus 2xi over the Wronskian xi. So you see that a resonance means that the transmission coefficient is non-zero, which sounds like the generic case, but no, because it is connected to the Wronskian like this. This is non-generic, okay? And the literature is full of these assumptions that let's assume V is generic. It means there is no threshold resonance, but our 3 models are resonant, okay?
So if I have a generic potential, nonlinear potential, I'm not going to have this resonance.
If you pick from a generic field theory model, you won't have this problem. So phi 4 is particularly difficult because it has the internal mode with the Fermi-Golden rule phenomenon, and it has the threshold resonance. Now, I'm doing horribly on time. So what should I skip? Where should I go? Let me write down, since I spoke about resonances, let me write down a very important effect of the resonance on the time evolution, right? What is the effect? I wrote down that the Luehrmann expansion of the resolvent starts with a singular term. What this means on the level of the evolution is that if you take data called and you subtract a rank 1 piece of the evolution, that rank 1 piece of the evolution looks like the time evolution of that rank 1 projected. It's either covered or which I read. So you e to the I pi over 4 divided by root t, which is the stationary phase type decay in 1D. And then you have phi tens of phi acting on V. You put this in L2, and then you get better decay. You get t to the 3/2 decay, albeit in more than L2. Okay? And H is exactly what I had. This H is this. And you need to assume a bit more. But again, V Schwartz is good enough. PC, they project on the continuous spectrum. This +1 is present in all our models. Because if you don't add it, then you look like the wave equation. But the wave equation on the line has no decay. The reason for this is that the dispersion relation of the wave equation is a pair of lines that has no curvature. But the dispersion relation of root 1 plus psi squared is just, these are just hyperbolas. They have curvature that decays like an inverse third power of psi, but it's non-zero. So the striking feature, you have a rank 1 effect, and this rank 1 effect is detrimental in these models. On the other hand, it has an essential effect on the dynamics. There is another estimate that I should write down, which governs the nonlinear theory. Very basic, is the project on the continuous spectrum. Then you take F, L infinity, decays like root t, you cannot do better than this. And then you have here 2 derivatives in L1. So write d squared F in L1, where d is minus I LF, the momentum operator, okay? So that's the standard dispersive estimate that you see just from harmonic analysis, stationary phase, chopping up into dyadic frequency blocks. This is a totally different creature. That is in a paper of Hans. So Lindblad, Luehrmann, Soffer, and myself from around 20, okay, where we made use of this for a very important purpose. So let me write down two theorems. So what about the asymptotic stability theory for sine-Gordon? Since it's completely integrable, somebody should have done the inverse spectral, right? Inverse scattering method for it. And this happened surprisingly recently. Chen Liu Lu wrote a long paper where they applied complex methods, Riemann-Hilbert, D-bar, steepest descent, you name it. And so they obtained a striking result. So one would think it had been done before. For generic data, they have everything. They have Soliton resolution. Everything one has to be careful. So Soliton resolution and asymptotic stability which means that you can write your solution phi, the field, as a superposition of moving and Lorentz transform kinks. So these are kinks, Lorentz transform. So you have a velocity x minus vjt, and you can choose kink, anti-kink. There are finitely many of them. Then they have a sum. Don't ask me to write those down. Breathers. What are breathers? They are localized solutions that are periodic in time. They can also move. So you have a bunch of those, and then you have radiation. But you have to be very careful what you mean by radiation. It decays in L infinity like this. However, you don't have scattering in the standard sense. You don't have wave operators. So the free evolution is a bad approximation to the scattering because of a long range effect that I'll get to in a moment. So this decays to 0 in L infinity like t minus a half, but it has a logarithmic phase correction, just like the linear wave operators with one of our potentials have logarithmic phase corrections. Okay. So let me write down a few results, otherwise I can't get to the new stuff. By 21. So now they have, by complex methods, inverse scattering transforms, the sine-Gordon. This is sine-Gordon. I said it but didn't write it, which is ridiculous. This is sine-Gordon. Now Luehrmann and I revisited this problem and wanted to use non-completely integrable methods. Why? Because for phi4, it's not completely integrable. So the big prize in this community is phi4. You cannot hope to use complex methods for phi4. So we need to develop, by means of model problems, techniques that might lead to a resolution of asymptotic stability for phi4. So theorem, and this is Luehrmann, who's a young mathematician at Texas A&M. This appeared in 21. And it says that if you take initial data for your, this is sine-Gordon. If you take initial data, which are kink plus a perturbation, and the perturbation has to be odd so that the kink doesn't start moving. Now we'll look at the moving kink in an ongoing project. And they have to be small, but they have to be small in a weighted, yeah, it's like this, H3, I believe, cross H2 less than epsilon. Then it follows that a field close to the kink will be bounded by root T. But in fact, we get much more. We can give an asymptotic description, albeit through some integrals, of the, including the phase, and the phase will exhibit a logarithmic phase correction. Why do I keep talking about the logarithmic phase correction? Well, let me remind you of the basic shape of the perturbative equation. It's like this. And for sine-Gordon, you have to keep going. Here, think of it, or look at this one. This guy looks incredibly dangerous and non-perturbative because if you write u times u, then this is 1 over root t times u. 1 over root t is hopelessly divergent because you're trying to do Duhamel formula, and ideally you want to see on the right-hand side terms of this form. And then you can integrate them to infinity, and you're done. But with something like this, so this is a big problem, okay? And ideally, you can use normal forms to convert it to a cubic nonlinearity, but you will see this is what happens for sine-Gordon. But here, if you write this in the form 1 over root t squared u, well, then you see you have a 1 over t potential that you cannot remove by normal forms.
Because your logs.
Then you get a logarithmic phase correction coming from here. Now, what is this miracle I just mentioned? That is an absolutely astounding thing without which we could never have proved that theorem.
Because you're using sine-Gordon or not?
This is strictly for sine-Gordon. But what do you mean by what you said?
You're using integrability somehow or not?
We're not exploiting integrability, but we're exploiting a miracle. And Luehrmann gave this a precursor to this talk at ISOM in 21. Capello was there. And tragically, Capello died. Awful. But I saw him just a few weeks before he passed away. And Capello's remark was he thinks that the vanishing I'm about to mention is a remnant of some expression of integrability, and he cited a paper from the 80s, which is in finite dimensions. Never mind. So it is absolutely possible, in fact, plausible, that the vanishing I'm about to mention. So forgive me if I just go on for a few minutes. I won't torture you too much longer, but I do want to say what the new theorem is that Luehrmann and I proved. It's 104 pages of a new paper. It will appear in archive in a few days. So, but 104 pages this day and age is short. Yeah, we're not talking about 1,000 pages. So what is the magic vanishing? It is the distorted Fourier transform, which is the Fourier transform of the linearized operator using these Yost solutions that I had somewhere of, just a second, alpha. What is alpha? Alpha, I said, is sech tanh. And then you have to multiply by phi squared, where phi is the resonance function of sine-Gordon. That's the solution to h phi. For sine-Gordon, the threshold is 1, so phi. In fact, for us, this phi is tanh. For this particular operator I had on the board, this phi is tanh. So what is that? At plus minus root 3 is 0. So what you're really saying is that, look at this, how crazy this is. Sech tanh cubed hat, no, I cannot write hat because this is the distorted Fourier transform. At plus minus root 3 is 0. This is this magic vanishing. And the magic vanishing is responsible for killing a small divisor. When you integrate by parts in time in the quadratic nonlinearity, I was hoping to explain all this, you will run into a small divisor exactly at these frequencies. These are the resonant frequencies. And why do they come up? Because you will see that you have an oscillatory term of the form IS2 minus root psi. And this is embedded in an integral of this form, T. And then you have here alpha hat of psi divided by SDS. Okay, I now mean distorted Fourier transform with a hat. And this grows like a log if this vanishes. But when does this vanish? It vanishes, what is this? This is root 1 plus psi squared. Yeah, well, when is root 1 plus psi squared equal to 2 at plus minus root 3? So these are precisely the frequencies for which this vanishes, and then that leads to a logarithmic growth. If this doesn't vanish, if it vanishes, you can integrate by parts and the small divisor disappears. That is the mechanism that allowed us, but there is, much, much more to do. So what's the new theorem? I guess I'm out of time. The new theorem is that we have, for the cubic nonlinear Klein-Gordon, a long time asymptotic stability result 2 times e to the constant epsilon minus 4, where epsilon is in the size of the perturbation. And because cubic Klein-Gordon doesn't have the magic vanishing, we have to use a much more refined norm that measures how close you are in frequency to this. And it's a lot of work to feed this microlocalization, if you want to call it that, into the quadratic cubic nonlinearities as the experts here know. And this result is for even data, all right? And it's only under a codimension 1 condition, which amounts that you are on a center stable manifold. All right, thank you very much. Thank you for your patience. Questions?
An obvious question. Is this optimal?
No.
I was going to ask.
No.
But you expect it to eventually break down.
Well, that's an extremely important question. Since you asked, I have permission to talk a little bit about it. Okay, and so the theorem talks about solutions of phi dt minus phi xx plus phi minus phi cubed. And the data are at 0 are the soliton plus a perturbation. This has to be even, because if it's not even, the soliton starts moving. And remember, the spectrum looks like this. For here you have a negative mode. In this negative mode, you kill with a center stable manifold. That is the translational mode, which is odd. You kill it with the even assumption. And you have no gap eigenvalues, and the resonance hits you in the face because you have even, odd, even. So you're not perpendicular to the resonance. And all right, what is it that we prove? We prove that our solution doesn't behave like this. We can only prove that phi minus q, this doesn't move, in L infinity is bounded by constant log t over root p times epsilon up to those times. This log is almost surely unavoidable because of work that, for example, Hans did with Luehrmann and Avi Sofer that showed that on these bad rays, you actually have this logarithmic slowdown. They did it for a quadratic linearity when there's no potential. Then I joined and I added the potential on the left, etc. So is this optimal? No. And how to go beyond that time scale? So if you were, there is no way to push our techniques even to e to the minus epsilon to the minus 1. But this is where you start seeing, this is where you lose the smallness. If this is epsilon minus 1, you lose the smallness.
So epsilon to the minus 1 is what you would guess you get.
E to the epsilon minus 1, then maybe you become of size 1, I don't know, okay? So we can't go beyond this barrier.
So this nonlinear Fourier transform, you're just Fourier transform.
This is the distorted Fourier
This is
transform.
the Fourier transform. This is basically using the
Scattering
eigenvalues of the Laplacian plus potential.
The generalized eigenvalues, the eigenfunctions, yes.
Yeah.
The scattering data.
Yeah.
Define your Fourier basis. Yeah. And we, to prove this, we don't work with a distorted Fourier transform because we do a Darboux transformation. We remove the potential on the left. We have to do it twice. Then you have a mess on the right, but the mess you have to control.
You don't use the Fourier transform.
We don't use the distorted, we use the free Fourier transform. Then this alpha changes, and this is the standard Fourier transform. This doesn't move. This is plus minus root 3 always. So you have a choice to use distorted Fourier transform or not. The reason that people have avoided it like the plague is because of the resonance. Because this happens, the distorted Fourier basis becomes discontinuous at 0 energy.
Mm-hmm.
But then last year, Gong Chen and Positeri found a trick, which is almost trivial, where they do this. Under symmetry assumptions that hold for these models, you can just redefine the Fourier basis so that it becomes continuous, and it is possible that we can avoid the Darboux transformation and work on the level of distorted Fourier transform.
So who successfully worked with this distorted Fourier transform?
Well, I have in the past, many people have worked with it in the past. an absolutely inspirational work for us for this new theorem is by Germain Positeri. It's a big paper that appeared last year, I think, in Forum Pi. It's also 180 pages long or something like that, with many details missing. And so if they add the details, I don't know, it's 300. Yeah, there is a remarkable work for, look, we go to this time. Elo and Masmoudi have a wonderful paper, 300 pages on 5-4, where they go up to times epsilon to the -4 plus a constant. And I don't mean e to that, I mean epsilon -4 plus a constant, very complicated.
You're going way beyond.
This is 5-4. And the reason that, well, 5-4 is just, that's a whole scary that I can't go into. So to approach 5-4, we would first have to do nonlinear Klein-Gordon for all times. Or there is a sensible project to try and push 5-4 beyond such times. Horrendously complicated, it seems, because of very delicate resonance phenomena. Okay.
But I'm slightly confused. So those results are for which equations? The ones that you are.
Mattel,
yes.
That is 5-4, when it is local.
It's the local.
This is false if you put R because energy is conserved. This doesn't get any smaller. The energy just goes.
Yeah, I understand. But then what is the goal in
L infinity. L infinity. To show that this in L infinity.
This in L infinity.
So what's the big question? This is the big question.
Right, in L infinity and on the whole line.
On the whole line.
Okay, I understand.
And you can absolutely, you would want to start with odd assumptions so that the kink.
So that doesn't.
Otherwise, it can't move.
Otherwise, the kink moves. You have the Lorentz symmetry in the problem.
Okay, but so if you don't start with odd, this would mean, okay, the kink moves, but could it be true with the kink moving? Like by doing this?
Yes. In fact, our one of the projects that we will start now, Luehrmann and Gongchen, we've been discussing it already, is the moving kink for sine-Gordon. So then you drop the oddness assumption from our 21 theorem. And well, then you have to do something.
Mm-hmm.
How do you know with what speed it's moving?
Next talk, next time. If you still want to hear it, yes, please.
We have a chance for some tea if we heard it.
So maybe the question at T, or just very quickly.
Just very quick, is the same kind of structure decomposition expected in the 5-4 model as well?
The Soliton resolution for 5-4, yes, probably, but that's extremely scary. The full Soliton resolution for the 5-4. Yeah, you would want to be able to say that every solution may be generic, but I don't see the need for genericity because for Chen, Liu, Lu, the genericity is essential. They remove in their theorem the wobbling kinks and other creatures, pathological creatures. This shouldn't have any pathological creatures. And yes, you should be able to say that every solution is global. So every energy solution decomposes into the sum of moving kinks plus radiation.
Mm-hmm.
But how to do such a thing at the moment?
Okay, Tom is eager to get tea. Let's make him happy.